Welcome to lecture number 9. So, let's see what we are going to do today. Let's see from the context of what we finished. Yesterday we plotted E versus K diagram. We got to the point where we could, last lecture we were able to reduce EK diagram into first Brillouin zone, and also I gave you an idea of what periodic potential would do by looking at one dimensional chronic penny model, and that one dimensional model told us that if we apply a potential which is neither too small in comparison to electron energy, nor it is too high, that means tending to infinity, then in that case we have a possibility of either having a metal where there is no band gap, or it is also possible, well, if it is some reasonable potential, periodic potential, in that case we could have a band gap opening up, and there is a band gap meaning disallowed energies for electrons. That means in states, K states where electron which electron cannot have. So, those are the, that leads to sorry, I rephrase my words, actually not disallowed K states, rather the disallowed energies. K states are possible, but there are certain energy, there is energy range which electron cannot have. So, that is what we call as band gap, and we saw periodic potential leading to band gap. So, now knowing that origin of band gap, and that we can use EK diagrams. So, in order to do so, using EK diagram, first thing I will do today is electron dynamics, and then we will again start looking at the classification of materials, and following that we will start looking at conductivity of materials in relation to the band structure. Let us see how far we go with respect to this particular topic, and then we will continue. If we do not finish, we will continue in the next lecture also. So, okay. So, let us start with electron dynamics. What do we mean by that? What we saw was that if I plot again energy versus K, if I again plot energy versus K, this is energy and this is within this first Brillouin zone. Now, I will always plot only everything in first Brillouin zone. In fact, it is symmetric, I did not need to plot both halves, I could have plotted only one half, but anyways, for sake of completeness, let us do that. What did we see? That we had two types of energy curves, one which was like this, after this nearly free electron theory, where we found that band gap opens up, we found, or let us draw it the way it was, we found that the curves were of these two forms. The shape of the curves was something like this. These are the two types of curves. We had either concave downwards or concave upwards, or you can talk in terms of convexity. But anyways, either way, this is the two types of curves for E versus K we saw. All right. Now, given these curves, this type of curves, what is the kind of information which we can get on motion of electrons from these curves? Can we derive anything from it? That is what we want to see, and that is what is called as electron dynamics. In order to do that, let us look at it in this following form. If I look at the total wave function, which is this total wave function, which is function of position and time, I have already said right up in front that I am solving for the spatial part. Time dependence is already assumed. We had said that this wave function would look like something like this. This is the quantity we have been all along solving, and we had assumed the time dependence to be of the form E j omega t. That is what we had assumed, and that is why we had separated the time dependent part of the Schrodinger equation from the spatial part of the Schrodinger equation, and been solving only the spatial part, because the time dependence form was already known, e to the power j omega t. Anyways, I construct the whole wave function, and the reason is that what we are going to see is that what first thing we want is, if we think of electron as a wave, the energy is transmitted through the group velocity. That means the velocity of the wave packet. If I look at the wave, so if I look at the group velocity, average, which is group velocity of the wave packets then that quantity is simply V is this is the velocity by which the energy is transmitted, transferred, is traveling. So, if that velocity is simply given by the dispersion relationship, that is del of omega by del k vector, which succinctly in another form can be written as gradient with respect to k of omega. So, you take gradient, that means this, if you want to expand it out further, then you can write it as del omega del k 1 x or x 1 plus del omega by del k 2, let us call it x 1 actually. So, this let us call it x 2 plus del omega by del k 3 x 3. All right. What does x 1, x 2, x 3 mean? I hope you understand. X 1, for example, in Cartesian coordinate system, where x 1 hat would be equivalent to x hat, and x 2 hat would be equal to y hat, and x 3 hat will be equal to z hat, meaning thereby that 1, 2, 3, or 1 implies x and 2 implies y and 3 implies z, meaning thereby that the three notations I am using 1, 2, 3 is really are the symbols of the orthogonal coordinates, which if it is Cartesian, then it is x, y, z, and in the way I have written expanded, of course, it is implied is Cartesian coordinate system here. So, therefore, x, y, z, that is how I have written the group velocity. So, that is the velocity by which, average velocity with which this electron wave is transferring energy. So, that is dispersion relationship which is given here. Now, why did I do this? What I really want to do is, this is what I want to determine. This is what I want to determine. Now, let us look at, I want to do it in terms of energy and k. However, I want to determine, because I want to relate it to this diagram here. This diagram is given here. I want to relate the velocity of electron through this diagram. So, in order to do so, let us see what is the energy operator. Let us go to the next page. Let us look at the energy operator. What is the energy operator? Energy operator, recall, was this operator was simply minus h bar by j del by del t. So, if I operate this, apply this operator minus h bar j to my del t to phi of r comma t, then I will get my, and I will get my energy times this wave function is what I will get. And what does the energy mean? Go ahead, substitute in there this wave function. This, remember, this dependence is e to power, time dependence is e to power j omega t. So, this is equal to phi r j omega t. Go ahead, substitute in there. What would you find? You will find that energy would simply be equal to h bar omega. Simply, this is the correlationship from this which will come out, that energy is equal to h bar omega. What does that mean? That means omega is 1 over h bar of energy, and therefore, this quantity, the velocity, average velocity, the group velocity would be equal to 1 by h bar of gradient of energy, or 1 over h bar, whichever way you like to write, of energy. In fact, I could write in indical notation, because I am going to use this very soon. So, I can write the component, the ith component, I being equal to 1, 2 or 3. I could write this as h del energy by del k I. I could simply write it like this, where I is equal to 1, 2 or 3. So, that is the component, velocity components written out in indical notations. Okay, so, that is a relationship. That is very important. So, what does that tell you? That tells you that if I have a E versus K curve, if I have a E versus k curve, then if this is the curve E versus k, let us say this is E versus k curve, then in that case, if a electron occupies a particular k site, if an electron occupies a particular k site, its velocity can be determined through this slope of E versus k curve. Slope of E versus k curve tells us the velocity. Notice what are we trying to do? At the end of the day, we have energy versus k relationship. Remember, k I have already said that relates to momentum. K is related to momentum, though I will prove this more clearly today. So, in principle, we can do the entire dynamics in terms of energy and momentum space. Now, since what we are trying to do is that since we are quite comfortable with Newton's law, which is force equal to mass times acceleration, this force being the external force which we applied, and against that I want to know what is the acceleration produced if I knew mass. Now, this is the relationship that I want to do, which is a classical particle would follow. Since I am quite comfortable doing this kind of dynamics, F equal to ma, what we have achieved as E versus k curve from quantum mechanical calculations, what we are attempting now to do is fit this quantum mechanical calculations into this form. Once we do so, then for future reference we do not need to start calculating based on E versus k, but lot of electron dynamics in that case can be done based on Newtonian type of mechanics. That is the interest, and that is why we are trying to define certain parameters here. So, in that context you can see that I can define a quantity called velocity, which simply is the slope of E versus k diagram. Of course, 1 by h bar factor is also there. So, we can take the slope of E versus k diagram and define the velocity. So, let us do that. Let us plot this diagram out first. As we go along, let us keep plotting it. What I am going to do is that I will take and draw a big line right in the center. I will draw a big line like this. Okay, then let us so let us plot this. So, what I am going to do is I am going within the first balloon. So, this is k axis. So, this is my k axis. This is k equal to 0, and this is, let us say, some direction k by 2 and minus k by 2, meaning thereby that I have drawn everything. I am going to draw everything in first Brillouin zone only. Remember, I already have, let me first plot the energy curves. So, energy curves are two kind. I have already talked about this. So, let us say the energy curves are something like this. So, energy curves have a form which is something like this. There is one shape and other shape. I am not looking at the scale, I am just showing you the shape of these curves. So, I am going to on top of this draw the other form of it also, which was something like this, which is inverted shape. So, that was like this. Slightly off. It has a shape like this, two shapes of energy. So, I am plotting right here, I am plotting the energy. So, now based on this, I can now start plotting velocity curves. So, if I plot the velocity curve, let me plot it like this. Let me draw another line like this. So, I draw another line here, which is this line, another axis, same k axis we are drawing, and on this now suppose I want to draw velocity. So, velocity is derivative of E versus k curve. So, we can clearly now start seeing the velocity. What happens is, if I look at the dashed line, so dash type of curve, then in that case we start with somewhere here and somewhere here and up to here, up to this point we have a maximum, or first the velocity as the slope is negative. So, velocity is negative. So, it goes something like this, goes through a maximum here and then goes through a behavior like this, and around here, right, corresponding to this point, corresponding to this point. This point is corresponding to this point, is where we will go through a maximum. So, this is the nature of velocity corresponding to the dash curve, where it is 0 here, it is 0 here, it is 0 here, and similarly I can draw it for the solid lines also. If I draw it for the solid line, again the slope is 0 here, slope is 0 here, slope is 0 here. For dash line I should have pointed here, here and here. So, now for solid line if I plot it, then same way for the solid line it will look like something like this, is how it will look like solid line, and this I have just plotted velocity. Remember, velocity is if of electron if a site is occupied. If it is not occupied, obviously there is no question of velocity then, though there is a relationship called something called E versus slope of E versus k curve. Though there is a slope of E versus k, but electron must be on that side to consider its velocity, to talk about its velocity anyways. All right, so that is the velocity. Let us proceed further a little bit. So, this is what where we were. We have just shown you the plot of this E versus k curve, which is the velocity, and now I am going to start looking at something slightly more. Let us look at what is the relation between external force. The keyword is external here, external force and quantity called hk. I have already given you the answer that this quantity hk represents crystal momentum, and I used the word crystal momentum earlier to suggest that it behaves as a momentum to an external force. This I just had stated much earlier. In free electron case, I said that hk is exactly the momentum of the electron, and in passing I said in general it is called crystal momentum, because in other cases also where hk not necessarily is the momentum, yet it behaves like a momentum to external force. What does that mean is what I am going to now show to you. If F is the external force, this is the external force. In that case, if external force that is applied, in that case, what is this quantity called V dot F? Clearly, that is rate of change of energy, that you know very well. Rate of change of energy is dE dt, not del E del t, but dE dt is what this quantity is. And remember what E is. E is a function of k, or expanded form you will write E as a function of k1, k2 and k3, 1, 2, 3 representing x, y, z, for example, in Cartesian coordinate system. All right. So, this is E, or k1, k2, k3 are in directions of x, y and z. So, that is the E versus k. So, if I want to calculate this, let us do that. So, let us write it down explicitly this time. So, dE quantity clearly is equal to del E by del k1 d k1 plus del E by del k2 d k2 plus del E by del k3 d k3, and therefore dE dt is del E by del k1 d k1 dt plus del E by del k2 d k2 dt plus del E del k3 d k3 by dt, which I could write as del E by del k vector dot dk dt. So, I can write this quantity as follows. Now, if I further introduce this 1 over h del E del k and dot product with h bar dk dt, and remember this quantity is equal to dE dt, which is v dot f. What do you recognize this quantity as? We have just shown that this quantity is nothing but v. So, what is this quantity? So, what is this quantity? Clearly, therefore, this quantity must be f. This quantity must be f, therefore. In other words, f is equal to h bar dk dt, total derivative, equal to h bar k d dt. So, hence h k must be the momentum whose rate of change is external force. I should say momentum like, whose rate of change is external force on an electron. So, it should behave like a momentum of the electron. However, it may not be the actual momentum of the electron. Whose rate of change would have given us total force, which, for example, includes forces arising from ion interaction. So, there are internal forces, for example, arising from ion interaction. So, that is what electron experiences. So, and F is the external force that is applied, total force is sum of these forces, rate of change of momentum, actual momentum is then equal to total force. But this quantity h k behaves like a momentum to an external force. So, its rate of change is simply equal to F, which is external force, x, which is just the external force, and hence we call this quantity as crystal momentum. And now I hope it becomes really clear that in case of free electron theory, since there were no interactions, there were no ion interactions, therefore the force experienced by electron was only the external force, and hence h k was also the actual momentum of the electron. But in general, h k quantity will not be the actual momentum, but just behave like momentum to external force. All right. With that said, let us move further and now start looking at the acceleration. So, if I want to look at the acceleration of electron, when external force F is applied. So, let's start looking at that. Acceleration of an electron when external force is applied. Now you see where we are heading towards. We are trying to find a relationship. We are trying to find a relationship between relationship of time F equal to ma for an electron in terms of EK diagram, because we have EK diagram. Given an EK diagram, I want to do the dynamics. EK diagram gives me all the information through quantum mechanics, which is what I want to do, and then I want to reduce it back to a classical like particle called F equal to ma, which follows F equal to ma, and hence my calculations will become easy. And so I am trying to fit that EK data into F equal to ma type expression. All right, so let us do that. So acceleration, as before, we will define as quantity called dv dt, and we already know what v is. So let us do that. Let us start doing this part. So now what I am going to do is I am going to start using indical notation. So let us start from here. What I will write is v of I being 1, 2 or 3 is 1 over h bar del E by del Ki. For those of you, again I keep writing here, who are more comfortable with vector notation, well, that quantity is simply del E by del K. If you prefer this way, then we can write it as follows. Anyways, or if you wish, which is equivalent to saying V is equal to 1 over h gradient with respect to K of energy. If that is the case, let us find the what this quantity is, dvi dt, total derivative we want to find out. Remember, we will do the same exercise as we did for energy in this page. On this page we did this exercise, we wrote dE and then we calculated total derivative through this expression. In this expression, now instead of total derivative of energy, we are going to take total derivative of del, this whole quantity here, this del E by del Ki. We will take the total derivative of this with respect to time, and will therefore replace energy by this whole quantity in there. So in that case, I will write therefore dvi dt as equal to 1 over h bar d dt of del E by del Ki, and therefore we are going to take the total derivative of it. So what do we do? So same way we will write this as 1 over h bar, and since we want to take total derivative, so we are going to write this as summation over j, which goes as del by del Kj of this quantity del E by del Ki is what we will do here. So if you want, I can write this as vector here dv dt, therefore we write it as 1 over h del E by del K and d dt of this quantity, and I can write this as equal to 1 over h bar d dt of this quantity, and I should write also simultaneously with this a dkj dt. Notice I have done basically same thing. I have taken essentially expanded out, I have written dE, and in this I have replaced E by del Ki, and then of course you can see this is then del by del K1, del by del K2, del by del K3 and dk3 by dt, which is what exactly I have done here, that the summation is over j. That means j takes a value of 1, 2, 3. So you can sum this over j equal to 1, 2, 3. So j equal to 1, 2 and 3. So this is this quantity is now changing the order of differentiation. Changing the order of differentiation, I can write this quantity as dvi dt as equal to 1 over h bar summation del square E by del Ki del Kj, j sum being conducted first, and dt. If I write it like this, then I can further write it like this as 1 over h bar square. I made it square now, and this summation is over j. And what I am going to do is I am going to take this del by del k I out, del by del k I out, and I am going to write this as summation over j of what quantities? Del E by del kj and d kj by dt. So, this is the quantity, and remember, sorry, h bar also should also be put in there. So, I should put a h bar in there. As this quantity. So, now clearly what do you associate this with? This quantity is simply the jth component of the force, j component of force. So, force is 1, 2, 3, remember the h dk dt is the force. So, this is the jth component of the force. So, I can write this as, and remember this has been possible because this force does not depend on ki. So, its derivative with respect to ki is 0. This force is the external force. So, I write this as 1 over h bar square del by del k I, and I am going to write this quantity therefore as summation over j of what? Del E by del k j f j. Now, I am going to write it, or alternatively I will write this as 1 over h bar square del by del k I of, I am going to write this as now dot f. I am going to write this as dot f, which is this is the gradient taken with respect to k. Here is the gradient taken with respect to k, and dot f will give me this summation quantity right here. These are the three components I am going to get. So, all right. So, if I get this, now this I can of course write as also, this I can write in a different form. I can, in a vector form, I can write it this as 1 over h square gradient with respect to k of all right. That is what little algebra was, but what you see? What you see is that something interesting, that you can begin to see from right here, either right here or right here. Either of these 2 points you can right here or right here. Just focus your attention here. What does that mean? Notice that I can write therefore a I component of acceleration is equal to 1 over h square del by del k I times summation over j of del E by del k j f j. I am basically reproducing this equation here. I am basically reproducing this equation right here. What does that mean? That means that acceleration in direction I being 1, 2, 3, so x, y, z if you wish, is produced by forces which are not necessarily in direction I. So, that means since j can take value of 1, this j can take a value of 1, 2 or 3, therefore, a force in direction 2 or direction 3 will also produce an acceleration which is in direction I. So, that is the difference, and that is what you need to keep track of. So, if you keep track of this, the way we will do it is as follows. Therefore, I am going to define this quantity a I. We use this equation right here. We will use this equation right from here itself. Let's pick it off from here. Let's take it off from here. 1 over the dv di acceleration, this a I quantity, as being equal to 1 over h del square E by del k I del second derivative del k I del k j d k j dt. Let us pick this equation from here. So, acceleration is equal to 1 over h, in fact I will make it 1 over h square del square E del k I del k j, and I will write now h bar of course d k j by dt, which is what it was. In this I have made this square, I have made this h square, and I have inserted a h right here. introduced a h here. So that's fine. That's the only thing difference I've made. So therefore, I'm going to write this as, and of course there is a summation, and of course there is a summation over j. Like you can see here, this summation right here. So this summation over j. So I can write this as quantity which is equal to summation 1 over h square del square E del k I del k j, this whole thing, times f of j, and this summation is over j. If so, let me define a quantity called Mij. What it means is, forget about it for a minute, that quantity let us define as 1 over or 1 over Mij, inverse of this quantity, let us define inverse of this quantity Mij as equal to 1 over h square del square by del k I del k j. Now, so if that is the case, I can write I substitute ai as summation over j, and then I can write this quantity as 1 over Mij Fj. So, what do you see? So, what we see is, remember, Newton's law or classical particle follows ai equal to Fi by mass, a mass. That is what a classical particle will follow. And essentially, therefore, I have just defined a quantity called effective mass. So, if I have E versus k curve, then it is a second derivative, once with respect to k I, other is with respect to k j, then gives me a component. Now, it is a 9 components. So, this is a tensor. So, this is rank 2 tensor Mij. So, essentially, therefore, I have something called this A1, A2, A3, the 3 components are equal to 1 over, of course, M11, 1 over M12, 1 over M13, 1 over M21, 1 over M22, 1 over M23, 1 over M31, 1 over M32, 1 over M33, F1, F2, F3. Now, I have got a behavior like a classical particle, except I have introduced a effective mass tensor, and this Mij, of course, is a quantity given by this. So, if I find, so essentially from E versus k diagram, now I can find effective mass. Once I know the effective mass, then I can also draw, essentially in that case I can also draw extract what the effective mass is. Once I have effective mass, then I can apply that to force equal to mass times acceleration kind of behavior, and then use it further. Except let us make a small simplification. If we use principal axis, in that case Mij I not equal to j vanish, and only Mii survives. That means only the diagonal components survive if I choose the principal axis. So, if I choose, in fact, that is the definition of principal axis. So, if I choose the axis such that only the diagonal elements survive, in that case I can write, and in fact let me put a star in here to denote that this is not electron's mass necessarily, but it is represents essentially a effective mass. So, in that case I can define effective mass Mii now, since we have only diagonal components. In that case I can define this quantity as 1 over h bar square del square E by del k I inverse, of course, of this inverse of this k I square second derivative. So, that means inverse of second derivative of E versus k curve gives me the effective mass of an electron. Effective mass of electron meaning that mass which can be put into force is equal to mass times acceleration kind of equation. So, that is what. So, now let us go back and start plotting all these quantities in there. If this is the velocity, then I can plot acceleration. So, let us plot acceleration as derivative of velocity. So, let us do this plot first. So, let us draw a line right here. This is a line for drawing my acceleration. Then clearly in this case the solid line will behave, I have derivative goes to 0, derivative of velocity goes to 0 here, and derivative of velocity goes to 0 here. So, it is going to go to 0 here and it is going to go to 0 here. So, I am going to draw this like this. The solid line goes therefore something like this. The acceleration therefore behaves something like this. And for the dotted lines, for the shape of energy curve like this, then this behaves somewhat like this, where the maximum, minimum and zeros are. This is my acceleration. This is what I have plotted as acceleration. Now, of course, you know that I already said that if you take the second derivative h square del E by del k square and take inverse of it, and inverse of that, then that gives me effective mass. That gives me effective mass of the electron also. So, let us plot effective mass of the electron and let us do that right here. So, how does that behave? Let us put it right here. And how does that behave? So, let us see, and in this case also right here are my 2 points here. What happens? Where does the slope goes to 0, this slope second derivative of E, remember this represents acceleration represents. So, this acceleration is a quantity which is equal to essentially second derivative. Acceleration is the second derivative of velocity or second derivative of energy. So, this is the second derivative I have plotted. Second derivative of energy versus k curve. Remember, that is what energy was acceleration, and if I take inverse of that, then that gives me effective mass. So, wherever it goes to 0, wherever this second derivative goes to 0, that is where I am going, effective mass is going to go to plus infinity or minus infinity. That means, wherever 0 is here, something will happen, because I need to take inverse to calculate the inverse of this curve. A curve is what I am basically trying to plot. So, let us do that for solid line. So, then now as we go along, this second derivative is decreasing. So, inverse of this along this solid line from here to here, this quantity is second derivative is decreasing. That means, inverse of it would be increasing, and here it would be going towards infinity. So, if I draw it like this right here, some dotted lines here, some dotted lines here, some dotted lines here, then what I should see is a behavior where somewhere this should go and go towards, shoot towards infinity. Similarly, what should happen if I look at, and similarly should happen on this side also, that it is decreasing along this side, it is decreasing, therefore, inverse of it must be increasing. But what about here? On this side, I should have, as I am going this way from here, as I approach from here to here on solid line, this second derivative is increasing. If second derivative is increasing, then then inverse of it should be decreasing. So, that means that my behavior here should be something like this. And similarly, on this side going towards minus infinity. So, the second derivative or this effective mass that I am plotting here, effective mass that I am trying to plot here, m star is what I am trying to plot, has a strange behavior. And similarly, you can see for the dotted lines, I can draw it for the dotted lines, it will behave like exactly opposite of this. This is how it will be, and shooting towards infinity here. So, this is strange. At these inflection points of energy, versus k curves. Here is the energy versus k curve. At the inflection points, we find that effective mass shoots up towards either plus infinity or minus infinity. That is a strange behavior. So, remember, this is effective mass, this is not real mass of the electron. So, this is a fitted mass, so that we can use F equal to ma type of equation. And in this context, you see effective mass behaving in a strange manner. This has a consequence, and I will shortly in the next lecture, I will begin to explain what this consequence of this particular this kind of behavior of effective mass has a consequence, and we will see, we will introduce a term called a hole also in order to explain some of these phenomena. And therefore, so what I would do is, now you can see that by having Ek curve, Ek diagram, I wanted to tell you what the utility is. There are a lot more utility in optical sides also, which we have to do, but on the dynamic side, you can say from you can see from E versus K curve, you can extract all the dynamical parameters, whatever is required for dynamics, F equal to ma type of dynamics, you can extract all that information from Ek diagram. That is the power of Ek diagrams, and hence we had been doing all along for so long this Ek diagram. Now, having done this part, now what I am going to do is start with showing you the Ek diagram and also the dynamics parameter. Let us start again with now classification of materials, which we have already done, but we repeat, and we introduce the idea of conductivity again, and in context of what we have learned from Ek diagram, what we have learned from dynamics and the behavior, the velocity, the acceleration, etc. In context of band diagram, after looking of classification of materials, then we start looking at the conductivity in relation to band diagram, and you will see we will use all these ideas together. So, let us start looking at classification of materials. First, we are going to define as metals, of course. It is clear, I am just repeating myself, which we did in yesterday's in previous lecture also, in the previous lecture as well. What we have in metals, we found that we had continuous energy levels available. We had continuous energy levels available. Second thing is that we had, for example, if you have an alkali metal which has 1 electron per atom, then that I will go through the details of it in the next lecture again, then it will fill the band partially. If it is a continuous band, then it is filling up completely. If I have a continuous band, then I have a very wide band available. That means all allowed energies are there. When I start putting electrons on them, I put electrons up to a certain level. After that, I run out of all the electrons. All the other energy states are empty. The point is that is a partially filled band, that is not completely full. That has a consequence. Metal, I am saying, has large conductivity because of that reason. Second, therefore, I will start looking at what is an insulator. You already know insulator is a material which has very, very low conductivity. It cannot conduct. So, what does that mean? That means that insulator, and I should see it in context of semiconductor itself, a conductor itself, both of these necessarily have a band gap. That means this is allowed energies, these are the allowed energies right here, and these are allowed energies. These are allowed energies and these are allowed energies. In both these systems, we find that electrons fill up to this level. That means one of the band is completely full, completely filled band at 0k, at least at 0k, completely filled band here, a band gap, non allowed energies, and an empty band. Such a material is always insulator. Such a material is always insulator. Remember, unlike partially filled band, I have a completely filled band, though there is an empty band, but there is a separation between them through a band gap right here, which we did not have in case of metals, but here we do. we have a gap in there, and this band is completely full up to this point, it is empty here. Consequence of that is that this material cannot conduct its insulator, and that I need to explain to you in terms of when I explain conductivity in terms of, but I am just classifying the materials and I am telling you the features of it, and you will see because of these features certain materials will be insulator and certain materials will be semiconductors, certain materials will be metals. If somehow at some high temperatures some electrons are able to jump, make a jump from here to here, then what do we have? Then we have this band also becoming slightly partially empty if you wish, because some electrons have left. There is some, therefore, it is not completely filled band. Similarly, this is not, since some electrons have jumped from here onto this particular band, therefore, this particular band is now not completely empty, but have some electrons in there, and in such a case we start getting some conductivity, and those are the materials which we call as semiconductors. If however, this gap which is here is very large, if this gap is very large, for example in diamond which is 5.3 electron volts, in that case even room temperature or some higher temperature is not sufficient enough to cause this electron to jump from here over to this empty band, and as a consequence this material continues to remain insulator. So, semiconductor or insulator is a relative term. At 0 K all of these will be insulator, and you go to little higher temperature, say room temperature, then in that case, in case of semiconductors, since this gap is small, some electrons can jump over. Both these bands therefore become partially filled. This one on top and one bottom become partially filled because some electrons have left, and hence they begin to conduct, and hence we call it semiconductor. Whereas in case of insulator, since this jump will not be possible even at room temperature, and hence it will not be able to conduct. Now what I need to do is in next lecture establish for you that why so. Why is it that only partially filled bands conduct? So, okay, that we will start with in the next lecture. Thank you.